All right, I am going to do an example problem. This is problem 43. It's not an even numbered problem, but it's problem 43. It's a series RLC circuit, and it has a lot of the elements that I want you to know. So we'll be performing it. Let's share the screen. This is on my iPad. So let's let it come up. And so a series RLC circuit contains the following components: a resistor of 150 ohms, an inductor of 0.250 henries, a capacitor of 2.00 microfarads, and a source with delta V max equal to 210 volts operating at 50 hertz. Our goal is to find the phase angle, the power factor, and the power input for this circuit. So these are the parts that we're going to be doing. A, find the inductive reactance in the circuit. B, find the capacitive reactance in the circuit. C, find the impedance in the circuit. D, calculate the maximum current in the circuit. E, determine the phase angle between the current and source voltage. F, find the power factor for the circuit. And G, find the power input to the circuit. Okay, so this is our given. R equals 150 ohms, L equals 0.250 henries, the capacitor is 2.00 microfarads, and the source is the Vmax is equal to 210 volts at 50 hertz. So let's start off with the inductive reactance. X sub L is equal to omega L equals 2 pi FL. So X sub L is equal to 2 pi times 50 times 0.25. That's 78.5 ohms of inductive reactance. Now, what are the units? The units are cycles per second times henries are volt seconds per amp. So the seconds cancel and you end up with volts over amp. That's equal to ohm. Disregard the cycles. Okay. Capacitive reactance. X sub C equals 1 over omega C, which is equal to 1 over 2 pi FC. So for this case, X sub C is equal to 1 over 2 pi times 50 hertz times 2.0 times 10 to the minus 6 farads. And if you multiply that out, you get to 1592 ohms or 1.59 kiloohms of capacitive reactance. Now let's do the units on this. We have 1 over cycles per second times farads. Well, farads are coulombs per volt. So that leaves you let's invert that, so we end up with volts over coulombs per second, and coulombs per second are amps, so it's volts over amps, and that also is equal to ohms. Okay, the impedance Z is the square root of R squared plus X sub L minus X sub C quantity squared. So let's put in those values for Z. It's 150 ohms squared plus 78.5 ohms minus 1590 ohms squared, quantity squared, you get 1520, 1,520 ohms, and that's 1.52 kiloohms. Okay, D, the max current, Imax is equal to Vmax over Z. So Imax is equal to 210 volts divided by 1.52 kiloohms, and that's equal to 0.138 amps or 138 milliamps. The phase angle, phi, is equal to the inverse tangent of X sub L minus X sub C, X sub L minus X sub C over R. So that's the tangent inverse of 78.5 minus 1590 divided by 150. And if you put that in, you'll get 84, minus 84.3 degrees. Now, if you look, let's use black. If we have, this is our this is X sub L over here, this is X sub C over here, and over here is the real part. So the angle has to be from, there's only a first and fourth quadrant here. So if it's predominantly inductive, it's going to be a positive angle. If it's predominantly capacitive, it's going to be a negative angle, and that's why we get minus 84.3. We don't have to worry about it might be 256 or something like that. It's going to give you, if you put it in your calculator, it should return a value between pi and, I mean, not pi, pi over 2 to minus pi over 2. So let's get rid of that. Oops, I should do it in this mode. Okay, that's easier. All right, so we got minus 84.3 degrees. If you, I forget what it is in radians. I think I came up with minus 1.47 radians or something like that. Let's see if I know you won't see it on the screen, but I have it. Let's see, that one, that was for E. Oh, I don't have it in radians. I think it was like minus 1 point something radians. You need to make sure that you have it in, you have your calculator set to degrees and not in radians, because you'll think you got a low angle, but it's just that you're in radians and not in degrees. Okay, now for F, the power factor. Power factor is just cosine of phi. So the cosine of minus 84.3 degrees is equal to 0.0988. 84 is almost minus 90, so it's going to be a very, very small number. In other words, it means that the horizontal component, cosine is always going to be along the x-axis. So 0.0988, it means it's a very, very large, a very, very small component. And indeed, I'm going to do a graph in a bit, and you'll see that that's the case. Okay, so that was a power factor. So the power input is equal to power is equal to IRMS delta VRMS times the cosine of phi. Now you can do it 0.707 times 0.138 amps, or 0.707 times 210 volts times the cosine of minus 84.3. I prefer using the square root. So P is equal to 0.138 amps divided by the square root of 2. 210 volts divided by the square root of 2 times cosine of minus 84.3 degrees equals 1.43 watts. 1.343 watts. Now, this is what I want to show you, and I might have to make it smaller so that you see. And it was unfortunate that these values were what they were, because they're quite a bit off scale, but you can get the idea. So this over here is the X sub L, this upper port, that's the X sub L, just 78.5 degrees. This down here is the X sub C, it's 1590. I said degrees, I'm sorry, 78.5 ohms. This down here, the X sub C, is 1590 ohms, 1590 ohms in the negative direction. That's why it's X sub L minus X sub C. So we have this X sub L minus X sub C. So it probably isn't to scale, but the X sub L minus the X sub C, there's the X sub L. It gives us this component there. This here is the downward component, and you take the square root of the sum of the squares, the R plus the X sub L minus X sub C squared. You get a 1520 at an angle of minus 84 degrees. So this is the resultant impedance. This is the impedance. This purple here is the impedance. The blue is the real. The red is the inductive reactance. The red in the downward position is the capacitive reactance. The blue is the real, and the purple is the resultant. So I think that's all I have to discuss on this part here. I'll have my Mathematica calculation so that you can see what I did to calculate these values. But I think that's it for explaining this problem. I wanted to go in this problem in detail because I think it shows what we're doing in these types of problems. Hopefully this helps.